Hi, chemistry students. It's Mr. Gopal here with a really interesting lesson on atomic emission spectra. So you might recognize the root of the word spectra. Spectra comes from spectrum, and specifically the spectrum that I'm talking about, and the spectrum is usually a range of values. The spectrum that I'm talking about is the light spectrum, all right? One thing that you're going to pick up eventually in chemistry and also take a look at when you examine light in physics is the fact that light, even though we tend to see it as white or I guess like a yellowish hue, there is a spectrum of light, all right, depending on the wavelengths of that light. And that spectrum will manifest as colors, okay? And the other interesting thing that we need to talk about is those colors can often indicate the elements involved, okay? So when we talk about chemistry, we can subject different elements to certain conditions, and they will reveal a different light spectrum, a unique light spectrum. And so the focus question here is, how can we use atomic emission spectra to identify an element? As I said, they're unique spectra, all right? And they come from exciting the electrons in an element. So when we excite them, they absorb energy and they jump out of their ground state, which is their stable state. You may remember from previous lessons that in a stable configuration, the electrons are grouped in certain energy levels outside of the nucleus, and that is the most stable state for that atom. However, we can excite them by adding energy, all right? We can do this in multiple ways. So one way in which we do this is by passing an electric current through a sample of the gaseous version of an element. So you can see some elements here. They happen to be noble gases. We have helium, neon, argon, krypton, and xenon all over here. I'm going to circle them in black. This area right here. And each one, as you can see, gives off a unique color. Heliums and argons are rather close, but we can see that argon's is a substantially darker purple than helium's, which is a light, almost white purple. Okay, so if we pass an electric current through a sample of, say, neon gas, we'll see this beautiful orange and dark, rich red color, all right? However, if we pass one through krypton, we'll see the faintest hints of purple, but it'll mostly be white. With xenon, it's going to be a bluish hue, and with helium and argon, as I said, it's going to be different kinds of purple. But that's not the only way. This makes me miss my chemistry lab because I would often do this demonstration with students when we had access to the lab and everybody was in person. So what I would do is I would light a Bunsen burner, which is a gas-induced flame. All right, so I've got this gas coming out of this structure right here that I'm circling. And then I would just use flint to spark a flame. And then I could hold up a sample of a certain element with tongs into the flame, and we would see the flame change color. Now, in both of these cases, whether it's electric current or heat, what I'm doing is I'm adding energy to that gas. And that energy allows the electrons to move to higher energy levels, or what we call an excited state. However, the thing is, the excited state is far less stable. So after it absorbs the energy, it has to emit the energy when it hops back down to its ground state. And we see this manifest as color. And the whole thing happens so quickly that the moment that I hold the element inside this flame, we see the flame change color. So it is being excited and dropping down instantaneously pretty much to our eye. Very interesting. But this is another way for us to differentiate one element from another, because every element on the periodic table, believe it or not, has a unique spectra. All right, and I say spectra because there are multiple colors in its spectrum coming together. And so another way that we represent this is that we have gas contained in a tube, all right? We pass that gas then through a slit, and it goes through a prism. Now, a prism is a special piece of glass that we can use to separate out the different colors of light that are passing through it, and they'll separate out at various wavelengths and therefore be at different distances from each other. So we can see here with hydrogen, represented by the chemical symbol H, I'm underlining it there, we see these three wavelengths of light. One's almost indigo, and then the next is purple, and then we have a light blue, all within, let's see, 486 to 410, within about 76 nanometers, which is a very small space from each other. However, then we see this lone red line in the spectrum. It's all the way over at 656.3. So I can tell multiple things from this. On the one hand, I can see that blue, purplish, and indigo colors are at a much more narrow wavelength, whereas red tends to have a large wavelength. This will come back to bear when you study the universe in greater detail, which you'll do in earth science and to a lesser extent in physics. But there's an idea with light that we see red shift happening in the universe. In other words, there is a reddish color being given off, and that's because, sorry, let me explain this a little bit further. There's a reddish color being given off by distant stars in the galaxy. And what that means is that the wavelength between our eyes and those stars is lengthening, okay? And because of that reddish hue given off, we can tell that the universe is expanding. So in chemistry, we're looking at very small things here on Earth. We're breaking things down to subatomic levels and understanding how atoms behave, just tiny particles. However, the same principles govern the light spectra that we see in the universe and tells us that the universe is getting larger all the time. Now, how does this manifest in a Regents? Well, we have questions like this that kind of simplify the whole process. So you can see at the top, I have wavelengths being measured actually in reverse from what we saw in the previous chart. They're being measured from larger wavelengths down to smaller ones. And we have a series of elements that are unidentified except for a letter, A, D, X, and Z, all right? None of which are chemical symbols. So we just don't know what these actual elements are. And we want to figure out, well, wait a minute, what's the bright line spectrum? It's a mixture of two of these elements. I want to figure out which two. So if I'm looking here, I need to take clues. I can see here at 450 that I have a line just to the right of 450. And if I look over here, there's only one element, and that's element Z, that tends to have this same line in it. So I know that Z has to be part of it. And that helps me narrow down my choices. Got A and X and D and X that I can eliminate because element X and elements A and D don't have that line in their spectrum. Now, if I'm working my way to the left, I see that I have this patch of 2 right here. It looks like it's, let's see, this is going down by 10. That's 490, 480, 470, 460, 450. So at 460 and 470, I've got lines. Looks like it's a dead ringer for X. But I can't come to that conclusion quite yet. Actually, it's not. Let me tell you why, because this X lines up with 480 and 470, whereas this lines up with 470 and 460. So I'm looking for lining up with 470 and 460. I can see the element Z lines up with 470, and so I'm just looking for something that lines up with 460, and that would be A by virtue of that line. Now we just want to check and make sure that the other lines match up to what we're seeing. So with A, the next one I see is at 500. And lo and behold, I see one right at 500. The next one I see with either is at Z between 590 and 580. And again, I have one right here that corresponds. Next one I see is an A, and it is at about 610. And I've got one at 610. And so on and so forth. These two, for example, are at 670 and between 670 and 660. And if I go to 670, I've got one here. And I've got one, I'm sorry, I misread those numbers. Yeah, 660 is here, 670 is here, and I've got 2 between 670 and 660. So if I go over to 650, 660, 670, I have these 2 here and here. Finally, I have one just after 700. Let's call it 705 because it's between 700 and 710. And I've got that right here. So those correspond. So I can safely conclude that the elements present in this mixture are A and Z. Now, that's an abstraction, all right? You're usually not going to have wavelengths clearly laid out for you in black and white on a piece of paper with a measurement. This is how you answer questions about bright line spectra on the chemistry Regents, which is valuable. However, what I do want you to take away from this is that we can excite electrons in an element, get them to jump to an excited and unstable state, and when they inevitably go back down to ground state, which is more stable, they will emit light, and that will be the energy that they're giving off after they receive it or absorb it, all right? And so every element has a unique spectra, all right, unique series of colors that it gives off. We see them as a combination, and they tell us lots of things. They can tell us, in this case, what the element is or the composition of multiple elements might be. When it comes to the universe, they can tell us that the universe is expanding outwards. So that's a little bit about bright line spectra. Moving forward in the chemistry curriculum, you're going to learn a little bit more about unique ways to differentiate elements. I hope this has been helpful to you, and I will see you soon.